Hello. Today I want to talk to you about magnets. Now, magnetism is one of those things that everybody has played with. You've probably stuck magnets on your refrigerator or played with magnetic toys as a child. Two magnets can attract each other or push each other apart. It seems like magic, doesn't it? Things moving without touching. But of course, it's not magic. It's physics. And like most things in physics, when you really dig into it, it becomes far more interesting and far stranger than the simple picture you started with. Let me begin with a question that people always ask. What is a magnet? Well, that's actually a very difficult question to answer properly. I could say a magnet is a piece of material that creates a magnetic field, but then you'd ask, what's a magnetic field? And I could say, it's the thing that makes other magnets move, but we're going in circles now, aren't we? This is a problem we run into all the time in physics. When you ask what is something, you're asking for it to be explained in terms of something else you already understand. But what if the thing you're asking about is fundamental? What if there's nothing more basic to explain it in terms of? Then all we can really do is describe how it behaves, what it does, how we can predict and measure it. We can't say what it really is in some deeper sense, because we've reached the bottom. There's nothing underneath to stand on. So let me tell you what magnets do, how they behave, and maybe from that you'll get a feeling for what they are. First, magnets have two poles, which we call north and south. Like poles repel each other, and opposite poles attract. If you take a bar magnet and bring the north pole near the north pole of another magnet, they push apart. But if you bring a north pole near a south pole, they pull together. That's the basic phenomenon everyone knows. Now here's something interesting. If you break a magnet in half, you don't get a separate north pole and a separate south pole. Instead, you get two smaller magnets, each with its own north and south pole. Break those in half, and you get four magnets, each still with both poles. You can keep going, breaking the pieces smaller and smaller, and you always get complete magnets with both poles. As far as we know, you can never isolate a single magnetic pole by itself. They always come in pairs. We call these hypothetical isolated poles magnetic monopoles, and physicists have looked for them, but we've never found one in nature. This is very different from electric charge, by the way. You can have a positive charge all by itself or a negative charge all by itself, but magnetic poles always come together. This is one of the deep mysteries of electromagnetism, and it's built into the fundamental equations that describe how magnetic fields work. Now, what creates a magnet? Where does magnetism come from? Well, it turns out that magnetism is fundamentally connected to electricity. They're not separate phenomena at all. They're two aspects of the same thing, which we call electromagnetism. This is one of the great discoveries of physics, worked out in the 1800s by people like Ørsted, Ampere, Faraday, and finally unified into a beautiful mathematical theory by Maxwell. Let me tell you how electricity and magnetism are connected. If you take a wire and run an electric current through it, a moving flow of electrons, that wire creates a magnetic field around it. You can detect this with a compass. The compass needle, which is itself a little magnet, will turn to point around the wire instead of pointing north. So moving electric charges create magnetic fields, and it goes the other way too. If you take a magnet and move it near a wire, you create an electric current in the wire. A changing magnetic field creates an electric field, which pushes the charges in the wire and makes them move. This is how electric generators work. You spin magnets near coils of wire, and you get electricity out. It's also how electric motors work, just in reverse. You put electricity into coils of wire in the presence of magnets, and the magnetic forces make the motor spin. So, electricity and magnetism are intimately related. Moving electric charges make magnetic fields, and changing magnetic fields make electric fields. They're two sides of the same coin. In fact, in Einstein's theory of relativity, which I'll talk about more in a minute, what looks like a pure electric field to one observer can look like a mixture of electric and magnetic fields to another observer who's moving. They're really just different aspects of a single electromagnetic field. But this raises a new question. If magnetism comes from moving electric charges and we can make magnets by running current through wires, where does the magnetism in a permanent magnet come from? There's no obvious current flowing in a piece of iron that's been magnetized. What's going on inside? The answer is that the magnetism comes from the electrons in the atoms. Now, there are two ways electrons create magnetic fields. First, electrons orbit around the nucleus of an atom. This is like a tiny current loop, and any current loop creates a magnetic field. So each orbiting electron is like a tiny little magnet. But there's something else, something even more important. Electrons have a property called spin. Now don't take this too literally. The electron isn't actually spinning like a top. It's a quantum mechanical property that doesn't have a good classical analogy. But this spin creates a magnetic field, just as if the electron were a tiny spinning ball of charge. In fact, the magnetic field from the electron's spin is usually larger than the field from its orbital motion. So every atom has electrons, and each electron acts like a tiny magnet because of its orbital motion and its spin. In most materials, these tiny atomic magnets point in random directions. Some point this way, some point that way, and on average they cancel out. The material as a whole isn't magnetic, but in some materials, particularly iron, cobalt, and nickel, something special happens. There's a quantum mechanical interaction between neighboring atoms that makes it energetically favorable for the electrons to line up their spins in the same direction. When all the atomic magnets point the same way, you get a big magnetic field from the whole piece of material. That's a permanent magnet. Now, even in a piece of iron, the atomic magnets don't all line up perfectly throughout the whole thing. Instead, the material divides into regions called domains. Within each domain, all the atomic magnets point in the same direction, but different domains point in different directions. If you could look at an unmagnetized piece of iron with some kind of super microscope that could see the domains, you'd see a patchwork. This domain points north, that one points east, another points south, and so on. They roughly cancel out, so the iron as a whole isn't very magnetic. But if you put that iron in a strong magnetic field, something interesting happens. The domains that happen to be pointing along the field grow bigger, and the domains pointing against the field shrink. The boundaries between domains move. Eventually, most of the material ends up with domains pointing in the same direction, and now you have a magnet. When you take away the external field, the domains stay lined up. That's why it's called a permanent magnet. You've actually rearranged the internal structure of the material. You can destroy this arrangement by heating the magnet up. If you get iron hot enough, above about 770 degrees Celsius, thermal energy shakes the atoms around so much that the careful alignment of spins gets disrupted. The domains randomize, and the iron stops being magnetic. We call this temperature the Curie point, after Pierre Curie, who discovered this phenomenon. Now let me talk about something that confused people for a long time. How does the magnetic force actually work? When you hold two magnets near each other and feel them pushing or pulling, how does one magnet know about the other? How does the force get transmitted across empty space? For a long time, people thought forces required some kind of mechanical contact. One thing pushes another thing, like billiard balls colliding. But magnetism and gravity work at a distance. There's no chain of contact between the magnets. This bothered Newton tremendously when he developed his theory of gravity. He couldn't explain how the force was transmitted, and he didn't like that. The answer came with the concept of fields, developed by Faraday, and then put into mathematical form by Maxwell. The idea is that a magnet doesn't directly exert a force on another magnet. Instead, a magnet creates something in the space around it, a magnetic field. This field exists everywhere in space, getting weaker as you go farther from the magnet. Then, when you bring a second magnet into that region of space, the field exerts a force on it. Now, you might say this is just playing with words. Instead of saying the magnet exerts a force at a distance, we're saying it creates a field, and the field exerts a force. Have we really explained anything? Well, yes, actually, because the field is a real physical thing. It carries energy and momentum. You can detect it with instruments. It propagates through space at a finite speed, the speed of light. The field has an existence independent of the magnets that create it. Here's an example of why this matters. Suppose you have a magnet and I have another magnet some distance away. If you suddenly move your magnet, I won't feel the effect on my magnet instantaneously. The change in the magnetic field travels from your magnet to mine at the speed of light. If we're a light second apart, it takes 1 second for the change to reach me. During that second, the information about what you did is encoded in the electromagnetic field traveling through space. The field is real. In fact, electromagnetic waves like light, radio waves, and X-rays are just oscillating electric and magnetic fields propagating through space. When you turn on a radio transmitter, you're shaking electrons back and forth in an antenna, creating oscillating electric and magnetic fields. Those fields travel outward at the speed of light. When they reach your radio receiver, they shake the electrons in that antenna, and you pick up the signal. Light itself is an electromagnetic wave, a self-sustaining oscillation of electric and magnetic fields traveling through space. Now let me come to something really remarkable, something that comes from Einstein's special relativity. I mentioned before that what looks like an electric field to one observer can look partly magnetic to another observer who's moving. Let me explain what I mean by this. Imagine you have a wire with positive charges that aren't moving, and negative charges, electrons, flowing along it. That's an electric current. Now, if you're standing still relative to the wire, you see the positive charges at rest and the negative charges moving. There's a current, so there's a magnetic field around the wire. If you hold a charged particle near the wire, it feels a magnetic force because it's a moving charge in a magnetic field. But now imagine you're moving along with the electrons, traveling at the same speed they're flowing. From your perspective, the electrons aren't moving. They're standing still relative to you, but the positive charges in the wire are now moving, going the opposite direction. You still see a current, but now it's a current of positive charges going backward instead of negative charges going forward. Here's where it gets interesting. Because of the effects of special relativity, when things are moving, lengths contract along the direction of motion. From your moving perspective, the spacing between the positive charges is slightly different than the spacing between the negative charges, because they're moving at different speeds relative to you. This means the wire, which looked electrically neutral to someone standing still, looks slightly electrically charged to you. So, what the stationary observer called a purely magnetic force, you, the moving observer, see as partly an electric force. The electromagnetic field looks different to different observers moving at different speeds. This is what we mean when we say electricity and magnetism are really the same thing. They're different aspects of a unified electromagnetic field, and which aspects you see depends on your motion. This is one of the beautiful things about relativity. It shows that phenomena we thought were separate, electricity and magnetism, are actually unified. The equations of electromagnetism actually contain relativity automatically. Maxwell's equations are already relativistic, even though they were written before Einstein developed his theory. When Einstein was developing relativity, the behavior of electromagnetic fields was one of his key guides. Now, let me talk about quantum mechanics and magnetism, because this is where things get really interesting. I mentioned that electrons have spin, and this spin creates a magnetic field. But in quantum mechanics, spin is quantized. It doesn't come in any value you want. An electron can have its spin pointing up or pointing down along any axis you choose to measure, but it can't point partway in between. It's discrete, quantized. This has strange consequences. If you take a beam of silver atoms and pass them through an inhomogeneous magnetic field, a field that's stronger in one region than another, the atoms get deflected by different amounts depending on how their spins are oriented. You might expect to see the beam spread out into a continuous distribution, with atoms deflected by all different amounts depending on the angle of their spin. But that's not what happens. Instead, the beam splits into two distinct beams, one deflected up and one deflected down. The spins are either completely aligned with the field or completely anti-aligned. Nothing in between. This is called the Stern-Gerlach experiment, and it was one of the first direct demonstrations of quantum mechanical spin. The quantum nature of spin is also responsible for some very strange phenomena. For instance, there's the Pauli exclusion principle, which says that two electrons can't be in the same quantum state. This is what gives matter its structure. It's why atoms have shells of electrons, why chemistry works the way it does, why you can't push your hand through the table. The table's electrons and your hand's electrons can't be in the same place with the same spin, so they resist being compressed. There are also purely quantum mechanical magnetic phenomena. One is called exchange coupling, which is what makes ferromagnets like iron work. It's a quantum mechanical interaction that has no classical analog. It comes from the fact that electrons are identical particles, and when you swap two identical particles, the quantum mechanical wave function picks up a phase. For electrons, which are fermions, swapping two of them multiplies the wave function by -1. This seemingly abstract mathematical property leads to a real physical force that aligns electron spins, creating magnetism. Another quantum phenomenon is superconductivity. In a superconductor, electrons pair up in a special quantum state, and these pairs can flow through the material without any resistance whatsoever. Superconductors have very strange magnetic properties. They expel magnetic fields from their interior, a phenomenon called the Meissner effect. If you put a magnet above a superconductor, the superconductor generates currents on its surface that create a magnetic field to exactly cancel the applied field inside. This makes the magnet levitate. It's a spectacular demonstration, and it's purely quantum mechanical. There's also quantum entanglement involving spin. You can create two particles with their spins entangled, correlated in a quantum mechanical way. If you measure one spin pointing up, the other will point down, no matter how far apart they are. Einstein called this spooky action at a distance and thought it showed that quantum mechanics was incomplete. But experiments have proven that this really happens. The spins are genuinely correlated in a way that has no classical explanation. This is now being used in quantum computing and quantum cryptography. Let me come back to a more basic question. Why do magnets come in north and south poles? Why not monopoles? This has puzzled physicists for a long time. The equations of electromagnetism, Maxwell's equations, are almost symmetric between electricity and magnetism. But there's one key difference. There are electric charges, positive and negative, but there are no magnetic charges, no magnetic monopoles. All magnetic fields come from currents, from moving charges. Some theories suggest that magnetic monopoles might exist, but they're extremely rare or heavy, so we haven't found them yet. Paul Dirac showed that if even one magnetic monopole exists anywhere in the universe, it would explain why electric charge is quantized, why charge comes in discrete units like the charge of an electron. That's a beautiful connection, but we still haven't found monopoles. Some physicists think they might have been created in the Big Bang, but then diluted to an incredibly low density as the universe expanded. Now, let me talk about something practical. How do we use magnets? Well, magnets are everywhere in modern technology. Electric motors and generators, like I mentioned. Loudspeakers and microphones work by moving coils in magnetic fields or moving magnets near coils. Hard drives store data as tiny magnetized regions on a spinning disk. MRI machines use powerful magnets to create images of the inside of your body. Particle accelerators use magnets to steer beams of particles around giant rings. The list goes on and on. One particularly important application is in transformers. A transformer takes electricity at one voltage and converts it to another voltage. They're everywhere in the electrical grid and in every power adapter. Here's how they work. You have two coils of wire wound around an iron core. You put alternating current into one coil. This creates an oscillating magnetic field. The iron core guides this magnetic field to the second coil. The changing magnetic field induces a voltage in the second coil. By choosing the number of turns in each coil, you can step the voltage up or down. The reason we use high voltages for long-distance power transmission is to reduce power loss. Power loss in a wire goes as the square of the current times the resistance. For a given amount of power being transmitted, using higher voltage means lower current, which means much lower losses. At the power plant, we step the voltage up to hundreds of thousands of volts for transmission. Near your house, we step it back down to the 120 or 240 volts you use. Transformers make this possible, and transformers work because of the relationship between electricity and magnetism. There's another application I find fascinating: magnetic confinement fusion. The sun produces energy by fusing hydrogen into helium. We'd love to do this on Earth because it would give us nearly unlimited clean energy. But to fuse hydrogen, you need to heat it to millions of degrees, so hot that it becomes a plasma, a gas of electrically charged particles. You can't put this in any physical container because it would instantly melt through. Instead, we use magnetic fields to confine the plasma. The charged particles spiral around the magnetic field lines and can be kept away from the walls. We're still working on making this practical, but it shows the power of using magnetic fields to control matter. Let me also mention the Earth's magnetic field. The Earth acts like a giant magnet, with a magnetic North Pole and South Pole. This is what makes compasses work. But where does the Earth's magnetism come from? The solid iron in the Earth's core isn't hot enough. Actually, wait, it's too hot. Above the Curie temperature, iron isn't magnetic. The Earth's core is definitely too hot for the iron there to be a permanent magnet. Instead, the Earth's magnetic field is generated by a dynamo effect. The Earth's outer core is liquid iron, and it's in motion, swirling and flowing because of convection driven by heat from the inner core. These moving currents of conducting fluid create magnetic fields. And here's the clever part. The magnetic fields affect the motion of the conducting fluid, which changes the currents, which changes the magnetic fields. It's a self-sustaining feedback loop. The kinetic energy of the Earth's rotation and the thermal energy from radioactive decay in the Earth's interior keep the dynamo running. Other planets have magnetic fields too, generated by similar dynamo processes. Jupiter has an incredibly strong magnetic field because it has a thick layer of metallic hydrogen, compressed so much by the enormous pressure that it conducts electricity. The Sun's magnetic field is generated by the motion of plasma in its interior. These magnetic fields can have dramatic effects. Solar flares and coronal mass ejections are magnetic phenomena, and they can disrupt communications and power grids here on Earth. Now, I want to come back to something fundamental. I started by saying that magnetism is strange. that forces acting at a distance seem mysterious. But actually, all forces are like this. Even when you push on something with your hand, you're not really touching it in the way you think. The atoms in your hand and the atoms in the object you're pushing are getting close to each other, and the electric fields of the electrons repel each other. It's electromagnetic forces, forces at a distance, that are doing the pushing. There's no actual contact in the sense of particles touching each other. In fact, all the forces you experience in everyday life, except for gravity, are electromagnetic. The strength of materials, friction, chemistry, biology, all of it comes down to electromagnetic interactions between atoms and molecules. Magnetism isn't a strange exception. It's part of the fundamental way matter interacts. At the deepest level we currently understand, quantum field theory, forces are understood as being transmitted by particles. For electromagnetism, the force-carrying particle is the photon. When two charged particles repel each other, we say they're exchanging virtual photons. This is a somewhat abstract and mathematical description, but it's incredibly successful at predicting the outcomes of experiments. In quantum electrodynamics, or QED, we calculate electromagnetic interactions by considering all the possible ways photons can be exchanged between particles. Each possibility contributes to the amplitude for the interaction to occur. When you add up all the contributions, you get predictions that agree with experiments to something like 10 decimal places. It's the most accurate theory in all of science. But even with QED, we haven't answered the question, what is a magnetic field in some ultimate sense? We've described how it behaves, how to calculate with it, what effects it produces. And maybe that's all we can ever do. Maybe asking, what is it really, is asking the wrong kind of question. I think the honest answer is that magnetic fields are what the equations say they are. They're a fundamental part of the mathematical structure we use to describe nature. And that structure is incredibly successful. It lets us predict and understand and build things. We can make motors and generators and computers and particle accelerators. We can explain how stars work and how the Earth's core generates its magnetic field. At some level, this is what physics is about. We build mathematical models of how nature behaves. We test those models with experiments. We refine them when they don't quite work. And gradually, we build up a picture of how the universe operates. Magnetism is part of that picture, deeply connected to electricity and relativity and quantum mechanics. It's one piece of a larger puzzle. And you know what? The puzzle is still incomplete. We don't have a unified theory of all the forces. We don't fully understand how quantum mechanics and gravity fit together. We don't know why the universe has the particular particles and forces it does. There's still mystery, still things to discover. But that's what makes it exciting. Every time we answer one question, we uncover new questions. Why do electrons have the charge and mass they do? Why is the speed of light what it is? Why does the universe follow mathematical laws at all? These are deep questions, maybe unanswerable, but worth thinking about. When you play with magnets, when you feel them pushing and pulling, you're experiencing something fundamental about nature. You're feeling electromagnetic fields, quantum mechanical spins, relativistic effects, all wrapped up in a simple everyday phenomenon. That's remarkable. The universe reveals its deepest secrets in the simplest things if you know how to look. So the next time you stick a magnet on your refrigerator, remember, you're not just holding a piece of metal. You're holding a piece of aligned quantum mechanical spins, creating a field that fills the space around it, interacting with the electrons in the refrigerator door through one of the fundamental forces of nature. You're holding a window into the deep structure of reality. And that, I think, is pretty wonderful. Thank you.